Hello and welcome back to Algebra, the video course where we talk a lot about groups and what we can do with them. And in today's part 15, we will look at examples of so-called cyclic groups. From the last video, you already know that these are not so complicated because a cyclic group can be generated by just one element. However, before we start with the examples, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that you can use the link in the description to get access to all the additional material for the videos. This is really helpful if you want to have some quizzes and exercises for the topics. And now without further ado, let's immediately start by recalling the definition of a so-called cyclic group. It's a group G that can be generated by just considering one element lowercase g from the group. This means giving just one generator is enough to get the whole group back. In particular, this means if the group operation is written as a multiplication, we can write the group as the powers of the lowercase g. So any element in our group is just a power of our lowercase g. And indeed, this immediately implies that a cyclic group has to be an abelian group as well. We immediately see that when we put two elements together. This means we have g to the power k and g to the power m, and we know this is just repeating the element g or the inverse of g. However, no matter which of the both cases we have, we know that we can simplify it. Namely, counting the elements gives us that this is g to the power k plus m. And then obviously we see that we get the same result when we change the order. So in short, since only one element spans the whole group, we immediately get the commutativity. Hence, all the examples of today have to be abelian groups. And I would say, let's start with the simplest one. And obviously, this is the trivial case where G is just given by one element. This is not so interesting because we just have our identity element E. However, also in this case, we can say that G is spanned by this one element E. However, it's worth mentioning that this is actually the only case where we don't need any generator at all. Indeed, there we could say that G is generated by the empty set. Simply because the subgroup that only consists of the identity element is the smallest possible subgroup that contains the empty set. So this is all we have to say here, because G is the smallest possible group anyway, and now you know it's also a cyclic group by definition. Hence, let's immediately go to more interesting cases, namely the integers z. And there we know that the integers form a group together with the ordinary addition. And now the question is, how many elements do we need to generate the whole group z? And there I don't have to tell you that when you start at 0 and you add 1 again and again, you get all the positive numbers. Hence, we immediately recognize that the number 1 is exactly our generator. Indeed, it also works the other way around by subtracting 1, so adding the inverse of 1. And that's already the whole proof, you just need to know how the ordinary addition works. Therefore, Z is a cyclic group and generated by the element 1. However, since the group operation is not a multiplication, we would not use the power notation from before. However, as you already know, for a repeated addition, we also have an abbreviation. Namely, there the multiplication operation comes in. In an abstract sense, this can be a little bit confusing, but it actually just works like the power notation from before. So instead of the repeated addition, one just writes k times the element 1. So this is a common abbreviation whenever the group operation is denoted as an addition. But now please don't forget our important result here. The integers with the ordinary addition form a cyclic group. And moreover, we also see that our single generator does not have to be uniquely determined. Namely, the number -1 does exactly the same thing as the number +1. However, you should see for the integers, these are the only two options for the generator, because these are the only two numbers where we can actually hit all the other numbers. Still an important result to remember, for a cyclic group, we could have some freedom for the choice of the generator. Okay, and now for the next example, let's go into the subgroups of the integers. These ones we already know, and they can be written as m times z for any natural number m. So you see we have exactly the same notation as before. We use the multiplication as a shortcut to write a lot of additions. So for example, we can consider m is equal to 3. Then we get the subset where we only have multiples of 3. And there we already know this forms a group with respect to the addition again. And now the result is it's also a cyclic group. And obviously our generator can be chosen as the given number m. Indeed, it's the same picture as before. With the number m, we can jump through all the numbers in our set. So everything here is not so complicated, but these are already very important examples of cyclic groups. And there please note that all these groups here have infinitely many elements. Therefore, with the next example, let's go to finite abelian groups. And there you already know some very important ones, namely the integers modulo m. For every natural number m, we already know that this is a well-defined finite abelian group. And now the question is this also a cyclic group? And maybe as a quick reminder, let's write down the elements for m is equal to 3. There we have equivalence classes of numbers, and one is represented by 0, the next one by 1, and the last one by 2. And that's it, we have exactly 3 elements in that group. And moreover, the addition of 2 equivalence classes is just defined by using the addition of the representatives. This means if you have any equivalence class given by the number k and you add up the equivalence class given by the number 1, then by definition the result is the equivalence class of k plus 1. And with that you already see it, we can also go through all possible elements just by using the one element. Hence also here we have a cyclic group and it's generated by the equivalence class of 1. So it works exactly like we have it for the integers, with the only difference that now we only need to cover finitely many elements. More precisely, we cover exactly m elements in our group. Okay, so you see, with these examples, we have already learned a lot about cyclic groups. Namely, no matter which natural number m you give me, I can give you a cyclic group with this order. And moreover, we can also extend that to n is equal to infinity as well. In other words, the existence for every order is guaranteed. Hence, there are a lot of cyclic groups, and you can give all the examples from above. Moreover, in the examples above, we have also seen that a subgroup of a cyclic group is a cyclic group again. In fact, this is a general result, which we can also prove in the next video. So I really hope we meet again and have a nice day. Bye bye.